Okay, so in the last lesson, we learned about the number e, which again is roughly about, let's say, 2.72. So now let's look at the natural logarithm. So logarithms we learned in advanced functions, but the natural part, the natural logarithm is new for us now. So let's go back to recall about regular logarithms. So I'm just trying to move this up. The inverse of an exponential function, the inverse of it is a logarithmic function. So for example, here's an exponential function, right? Exponential growth, y equals 5 to the exponent of x. State the inverse function in exponential form. So in exponential form, if I'm looking at the inverse and back to grade 11 as well, I'm just switching basically my x and y's around, right? So instead of y, I have x equaling 5 to the exponent of y now. That would be the inverse in exponential form. And then in the functions course in logarithmic form, the base of the exponent, the base of exponent form is the base for the logarithmic form. So if my base in an exponential form, my base rate is 5. So I want that to be the base for my log form. So I have y, right? And we want y as isolated so that we don't have to use, we don't want y as an exponent anymore. So I can have x as an exponent. So I would have y equaling log base 5 of x. Okay, so just recall that. So now we're looking at, now that we know e, right? So for the function y equals e to the exponent x, so my base is e, 2.72. So exponential growth, exponential form. The inverse in exponential form is, again, just switch your x's and y's. X equals e to the exponent y, right? We like to have y isolated, and the base is e for logarithmic form. So the inverse in logarithmic form, y equals, right? We have it as y equals log in base e, right, of x. So now I have this log of base e here happening, which we can see down here. The logarithmic function with base e, logarithmic of e, occurs very frequently, and therefore it has a special name called the natural logarithm. So the inverse in natural logarithmic form is, I can just write it out as, instead of when I see log base e, I can write it out as this ln of x. And it's just like, I'll show you down below, just like mowing the lawn. L-A, you would pronounce it as L-A-W-N, it's spelled L-O-N, ln of x. So I don't have to write the base of e. If I don't want to write the base of e, then I'm just, it's the same, means the same thing, just a different a form, right? So log of e is the same thing as ln, the natural logarithm. So it is therefore commonly written as ln of x instead of log base e of x. So just like I said here, it's pronounced ln of x, and you pronounce it like mowing the lawn, but that's how it's actually spelled. So let's go here and look at, we're going to look at a table here for any function y equals f of x. We're going to graph. We're going to take a look at the graph of the inverse function and how it's related to the regular function. Looking at the line y equals x, right, which is a diagonal line, which would be the reflection, right, line. We're going to look at a table of values for the inverse function. For the x and y columns, they will be swapped if I'm doing an inverse, right? So if I wanted to graph an inverse, I'm graphing my line y equals x, and I'm just reflecting it over this diagonal line. If I have a table of values, I'm just swapping my x and y columns. This is from grade 11. And if I'm looking at an equation, I'm simply just swapping my x and y variables, right, in order to get the inverse function. So here, comparing y equals e to the power of x and its inverse, because now we've just gotten to know this new number e. So our original here, I'll do it in 2 different colors. I'm just thinking maybe not to use black for when we graph. So let's do one as blue. So let's say our equation here is, just like we'll use our original as just like it's telling us, y equals e to the exponent of x. And the inverse, of course, is when I'm doing the inverse of an equation, I would just switch the x's and y's. So x equals, I'm going to give myself a little bit more room here, sorry. I'm going to write a couple things down. X equals, I don't know why I said, x equals e to the exponent of y, right? Or, and I can write that out as y equals log base e of x. And again, because that's log base e, we now know we can write that as the natural logarithm of ln of x. So really this is the equation that we'll be using to get used to the natural log. So y equals ln of x will be our equation that we're looking at. So this is exponential form. This is writing this, switching the notation to logarithmic form. And then because it's log base e, we're writing it as ln of x. So if I had a table of values, I got to remember to keep switching my colors here. I would have x first and then y, and I would use my, let's say, some negative and some positive numbers, right? This is what we usually use, -2 to 2. So again, this would be just showing you here e to the exponent of -2. So you have to use your calculator, depending if it's e to the exponent of -2, -2, and then you press e again, depending on how you do it on your calculator. You should have a value of, it doesn't say how many decimals. I've got 4 decimals here. So I have 0.1353. So just make sure you're getting that to know how to punch that into the calculator. So again, I don't need to write this every time, but then I have e to the exponent of -1, right? 0.3679. So it's up to you to pause this and make sure you're getting these on your own. E to the exponent of 0, well, anything to the exponent of 0 is 1. E to the exponent 1, well, we already know what e is, we said, was like 2.72, but if I'm using 4 decimals, I can just go to the last node at the beginning where I had those 12 decimal places, but 2.7183. And then e squared, e to the exponent of 2, just to say there, is 7.3891. Okay, so if I was doing the inverse of that, let's change to green. I would just be switching my x and y values. So be careful, because for you're switching the x and y values, but for your table of values, you're still going to have x here and y here. It's just that when you're writing it out, let me change the color. These columns are switching. So your x's are now your x's, what was your x's is now becoming your y's, and what were your y's are now becoming your x's. Okay, but you still put the table of values, because if you were to switch this as y and x, you're going to end up with this being the same, right? So just be careful with that. So my x values are what my y values are. So I can just go ahead and write the decimals down here. So 0.1353, 0.3679, 1, 2.71, 83, and 7.3891. And then for my y values, just -2, -1, 0, 1, and 2. So using these values, sorry, I'll have to clear this to get to the graph. Again, if I zoom out, I just feel like this would be so small, like hopefully you can even see this, or you're just listening if it's in class. At home, I think it's okay to see, but this is why I can't zoom out, I don't think, any farther than this. So I have to clear this to move up. You've got the table in front of you to compare it to, and then we can start looking at the chart down below. And in this case, I think I will zoom in just so you guys can see a little bit better. I'm just going to graph it first, and then we'll look at our y equals x line. So to graph it, the first one was in blue. So I have the point. I need to look at my x and y values here to see where I want to draw my x and y axis. So if I'm looking at my X values are going from -2 to +2, right? -2 to +2, and my X values though for the other chart, the one that I had that was green, needs to go from basically 0.13 to 7. So I need to make sure I fit to 7, right? So 7, 6, 5, 4, 3, 2, 1. Could be basically meaning my y-axis could be in the middle. Then if I look at my y values, again, I'm going from about 0 to 7. So I need to make sure I fit up to a +7 on y. If I look at the other y values, I'm from -2 to +2. So I just need to make sure that y can fit up to -2. So basically they could be centrally located, but I don't have a lot going on to the left-hand side of the x-axis. I'm just looking at my graph. There's no values less than -2, right? And same with y. So I could move the y-axis. I'm going to make this a little bit thicker and make it what? Just orange. I could move this over 2, 4, 3, 2, 1 to, let's say, right here. And same with my x-axis too, right? I can move that down because for my y's, I'm not going any smaller than -2. So same if that was like just to have a couple extra, right? -4, -3, -2, -1. Oh, that's off a little bit. Let's do another one. Perfect. And I'll just erase that. Boom. And label as the lines continuing up and down, left and right, x-axis, y-axis. And now let's go back to my blue color to go back to my left-hand side chart, my original function, y equals e, base e to the power of x. And I have, well, we should put our numbers in here. 1, 2, 3, 4, 5, 6, -2, -4. Again, I know I need to go up to 7 here. So 1, 2, 3, 4, 5, 6, 7. I don't think I'm going past -2 here, right? So there we go. So I am at -2 and basically 0, just hovering above 0, right? So basically still have it kind of touching the line. And then -1, again, a little bit bigger, but basically still touching 0. You can see it just slightly above. I'm trying to show 0 and 1. So hopefully that's ringing a bell from grade 11, right? Your exponential growth and decay always go through 0 and 1. And then I have 1 and that E number from 5.1, 2.7. So just under 3, right? Over 2.5. So 1 and that would be 2.5. So just over that. And 2 and under 7.5. 2 and 7.5, just under that, 7.3 right there. And again, I'm going to try my best here. If I make this thicker, will that be easier? So these values will never go into the negative y, right? So I'm going to be coming close and closer and closer and actually never touch 0, right? So just, I know it's hard when you graph, and coming up, and I've got exponential growth here, and it looks something like this, right? Y equals 2.7 to the exponent of x. Okay, so then I'll write that out. I think that would be fine to write that there. Y equals e to the exponent of x. Now in green, I will do my inverse function. So my inverse function is starting out at basically 0, just to the right of 0, and -2. So just to the right, still can touch that orange y-axis line. Same, just a little bit beside that, and -1 for y. So if I'm just a little bit beside that and then -1, I'm still very close to that orange line. Then 1 and 0. So x is 1, y is 0 right there. And 2.7 and 1. So x is, that's 3, 2.5, just over 2.7 and 1. We're right there. And almost 7.5, 5, 6, 7, 8. So 7.5, 7.3 right there, and up to 2. There we are. And again, hopefully it seems to work when I'm making it thicker. So again, my values here are never going to become negative x's. And if you can see here, they're going to come close and close to, let's say, a y value of 0, but they're never, and an x value of 0, but they're never going to actually equal 0, right? So it's like I have a vertical asymptote here on the y-axis, and I actually have a horizontal asymptote here on the x-axis, but we'll get to that. For now, let's just graph it. Okay, and it's going to continue. Again, I shouldn't have it curving like that. I should have it looking like it's getting closer and closer to that y-axis line. There we go. And this is, let's write it as ln, y equals, equals ln of x. So what do we notice about the inverse functions? If you remember, if I was graphing them, just to show you here, back to our first bullet up here, if I'm graphing them, the inverse function is a reflection across the y equals x line. That's what I wanted to show you. So hopefully I can line this up properly here. Like that. So let's draw my y equals x diagonal, 45-degree diagonal line. In red, I'm going to, hopefully this will work out, as long as I get it right here. So I'll 45, 45, 45, 45. It is going right in the corner. That worked out well. Right, and like that. There we go. So there is my y equals x diagonal line. And if you can look, it is a reflection. The points are exactly reflected across, right, the y equals x line, drawing the inverse. So that would be back to grade 11. So now using this graph, so have this in front of you again, I'll have to move this up to do the chart. We're going to be looking at our domain, range, x and y intercept, equation of the asymptote, and then we'll move on from there. So again, this is our original is blue and our inverse is our green. Blue, and let's zoom out here a little bit. Oh. Should be hopefully good enough so I can fit more in there. Oh, I can pretty much fit them all. Perfect. Can I go a little bit bigger just so that you can see a little bit better? Point of inflection. Yeah, here, domain. So here, what is my domain of the original function? So my blue function, if you can see, so here, let's just write it out kind of in blue. It looked like this, right? And my green, just to try to help you guys out, went roughly like this. Okay, and then here's my reflection line. So back to blue. So the domain, x is going to keep, it's very vertical, but if it continues on forever, it is going to start moving to the right a little bit more and x a little bit more. So for the domain, my x just belongs to the set of real numbers. X is going to continue on, right? Be careful. For the domain, be careful of the inverse function, my green one here. My x would continue on, but it's never going to go to the left of 0 there, right? And then it's continuing on right forever. So it's not going to cross the y-axis. So my x belongs to the set of real numbers, but such that x is, be careful because it's not greater than or equal to 0, because you do have a vertical asymptote there. It's just greater than 0 because it's going to get very, very, very close, but not touch 0, right? Let's go back to now, keep your eye on vertical up and down. We're talking about range of this guy. This is going to continue on forever, but this one is leveling out, right? It's not going negative y. It's flattening out and going horizontal, very, very close to x is 0, but it's not going to touch. So there's again a horizontal asymptote here. So we have y belonging to the set of real numbers such that y is greater than 0. And again, same reason, not equal to, right? Now keep your eye on the inverse function for range. So if you wanted to, if this kind of, because I feel like it's kind of messing me up to keep switching back and forth, you might want to do a couple of these just looking at the one graph and then go ahead and do the other side just looking at the other graph if that's kind of messing you up. So for the range, it is going negative forever, but again, here it's going to end up leveling off, right? And will it continue on? It's leveling off, but is there any restrictions if you go back to your actual graph? It could continue on going positive and higher along the y-axis. So I would say there doesn't look to be any restrictions there. So then y belongs to the set of real numbers only. What are my x-intercepts of my original function? Y equals base e to the exponent of x. My x-intercepts. If I look at it, remember this one doesn't actually touch the x-axis. And that's it. It doesn't touch the x-axis. It goes up from there. So NA or none, there are no x-intercepts. And for this green one here, it crosses the, I don't want to draw it, but it crosses the x-axis if you take a look at 1 and 0, if you see that. Go up to your graph at 1 and 0. Now let's switch and take a look at y-intercepts. Where does this original function cross the y-axis? So it crosses the y-axis at 0 and 1. Just be careful that it's not 1 and 0, right? X is 0 and up to y is a value of 1. And then here, our y-intercept of the inverse, right? Just change to green before I forget. Our y-intercept, again, it's going to come close to y, but not touch. And then on this side, it's going to the right of y, so there is no y-intercept. And if you remember again from grade 11, remember the values of the domain. The inverse has the same value in the range, and the value of the range for the original function is the value of the domain of the inverse. They switch. See that there? And also here, obviously, change your x's and your y's. Here, NA and NA, right? And here it's close, but again, 1 and 0 and 0, 1, just because we're talking about the x and y axis there, that those switch. Be careful. So the equation of the asymptote, we said for this graph is the horizontal asymptote, right? So there's a horizontal asymptote at y equals 0. And if we're looking at the inverse function, again, we've got a vertical asymptote. So let's just say vertical asymptote at x equals 0 is the equation of a vertical line. And again, just to put there, this would be a horizontal asymptote. Intervals for which the function increases. So we're looking at our, reading it from left to right, looking at our x values. So it's basically always increasing, right? So the intervals have increasing x values. So it's increasing all the way along x. It's increasing for all of my x values. It's increasing. Let's take a look at my inverse function. So it's increasing for all of the x values in its domain, right? Reading it from left to right, as my x values move to the right, it's just increasing and increasing and increasing, right? So I have here, I'm just using whatever my domain is now. So x belongs to the set of real numbers, but I have to say such that x is greater than 0. Because again, it's not increasing for negative x values because that doesn't exist here. That's just why I'm listing that. So then intervals for which the function is decreasing. Well, if we just said here from left to right, it's always increasing, then that would mean that it's never decreasing, right? And same here, from left to right, if it's always increasing, then it's also never decreasing. Critical points. So let's go back, wrap our head around critical points of the graph here. Critical points would be where my tangent line is 0, where my derivative I'm set equal to 0. Critical points, I don't have any turning points here in this original function. It's just increasing. So I don't have any critical points. And for the derivative function, same thing here, right? I'm increasing. It doesn't switch to decreasing here, right? Never happens. So that's telling me that I don't have any critical points. Intervals for which the function is concave up. Concave up is a smile, right? Here I'm smiling, so it's concave up the entire time, always. So you just use your domain. It's concave up for all of the x values. But for the inverse function, let's take a look. Concave up, this is looking concave down, right? This is looking like a frown. Let's say the left-hand side of a frown, but you're reading it from left to right. It's still concave down, so I'm not concave up there, so never. Intervals, so here we go. Intervals for which the function is concave down. Because this is consistently concave up, it's all a smile, then it's never concave down. And for the inverse function, this is always concave down. So if it's always concave down, because it was never concave up, I'm just using my domain there, right? So it's concave down for all of the x values, but again, x has to be greater than 0. So this is the same as my domain. So basically, again, these are similar, switching. Just switch never and never and switch here using what your domain values were. So points of inflection. Points of inflection is that twist, right, where it's changing from concave up to concave down. So I'm looking at concavity, and for my original function, my concavity doesn't change. It's just always concave up. It never switches to concave down, so none. And let's look strictly at my inverse function. If you remember, it was always concave down. It never switches to concave up, so that's none as well. So I don't have any points of inflection for this one. Okay, so let's go take a look at some properties, some rules of natural logarithm of our new ln. Properties of natural logarithms. So if I have ln of e is equal to 1. So if I was to look here, instead of ln, right? Instead of writing it as ln is equivalent to a log base e. But I said instead of writing it as log base e, I can write it as ln because it happens quite frequently, right? And then this is ln of x, this is ln of e, log base e of e. So whenever I have a logarithm base and it's equal to what it is of, whenever these are equal to each other, then it's always equal to 1. Or it's like saying e to the exponent of what, e to the exponent of what here is going to be equal to e, is going to give me e. So then that's just equal to 1. So again, this might be easier just to kind of memorize these. Ln of 0 is undefined. So again, if I was looking at instead of ln, if I was looking at my log base e of 0, right? Anything of 0 is undefined. So even if it was log any base 4 of 0, that would be undefined if you were to plug that in. So then therefore the ln of 0 would be undefined as well. Okay. So what if I had ln of e to the exponent of x? So ln of e to the exponent of x. If I were to write that out as a logarithm, so I would have a log, let's say base, so b, log base b, of a value to the exponent of n, then the power rule would tell me that I would bring that n out in front, right? And have n log base b of m. So same thing here. I would take this value of x, this exponent of x, and bring it out in front. So then I would have x ln e. And let's pretend we don't know what it's equal to. But I know that ln e from up above is equal to 1. So then that's like x times 1. So then therefore that would be equal to x, which is what we're saying here. Or just think of it also as the shorter version of if I have a ln and an e beside it. So ln of e to the exponent of x, it's kind of like the ln and the e cross each other out, and I'm just left with whatever the exponent is. Similar here, if I have e as my base to the exponent of ln of x, pretend we don't know what it's equal to here. It's they basically just for a shorter version here, they basically cross each other out as well. So I have an e to the exponent of ln of x, the e and the ln, same as the ln and the e here beside each other, cancel each other out, and then I would just have x equals x. Okay, so let's look at using our calculator here and making sure that we're okay with the calculator that we have. So let's evaluate to 3 decimal places. So use E on the, I know that E is equal to, let's say 2.72, but use E on your calculator. Okay, don't use this shorter form. So if I use, again, you might have to hit E and then squared, or 2 and then E. You should get a value of 7.389 rounding to 3 decimal places. So make sure that you have that so you know how to use your calculator. And then if I have 1 divided by E, again, roughly 2.72, but we're going to use the actual E, we should have 0.368. And again, you have to play around with how do I do the square root of E? Is it square root and then E, or then E and then square root? But you should have a value of 1.649. Okay, and then there's a few more below. Just moving this up. I'm going to zoom out so I can just fit all the rest in there. All right, so if I have ln E, well, if we go back up to the top, remembering our rules up here, ln of E is just equal to 1. Oh, right here for D. So that was an easy one. Ln of E is just equal to 1. The ln of 20. So again, we're looking for this button on the calculator, whether you hit ln and then 20 or 20 and then ln. You know that it's working properly if you get roughly 2.996. So again, we're still doing 3 decimal places there, rounding. And if I did the ln of -100, try that on your calculator. And what do you get? You should have on your calculator that's an error, meaning that it's undefined, right? So if we were to look at the graph that we have up above, y equals the inverse graph, y equals ln x, right? Y equals the ln function. So if we look at the ln, that graph looked like, again, because I have it cleared from up above, we had our, let's say, graph. We had our, this was the inverse one, so we had our diagonal inverse line, and this was in green, and it looked something like this, right? So if I look at the ln graph at -100 at an x value of -100, that doesn't make sense, right? It's never going, it's getting close to a value of 0 for x, but never going negative. So that would make sense why that would be an error there, right? All right, let's move into number 2. Simplify ln E to the exponent of x squared. So again, if we go back to, this would be like the third bullet, ln E to the power of x is just equal to x, whatever the exponent is. So we're expecting it to just be equal to x squared, but just to explain, right? Again, power rule would mean that I'd move that x squared out in front. So I would have here x squared multiplied by the ln of E. Ln of E is equal to 1. So x squared times 1, and there we go, it's equal to x squared. But you don't have to put, again, all those steps if you just know that when I have, remember, ln of E just crosses each other out, and you're just left with the exponent. So here, ln of E plus ln of E squared. So if you remember what we just said, ln of E, the very first bullet, is equal to 1, plus, we just said, ln of E cancels each other out, which would be plus 2, which equals 3. But just to go slower here, we'd have the ln of E equaling 1. And then again, if we were to put the 2 in front, 2 times the ln of E, but ln of E is 1, 2 times 1 is again how we get to 1 plus 2 equals 3 there. Okay, what about the ln of e to the exponent of 2x divided by the ln of e to the exponent of x, and they have brackets around them, though, again, if you have ln e with brackets, just saying that the brackets don't really matter, and they're just setting that restriction there. So again, when you have ln and e beside each other, they cross out, so you're left with 2x over x, the x's cancel out, and you're just left with an answer of 2. Nice and easy, right? Here, e to the exponent of ln 2x multiplied by the ln of e to the exponent of 2x. So we've got e to the exponent of ln. Do I have anything like that up above? E to the exponent of ln is just the e and the ln cancel each other out, right? So let's go back to right here. Oh, complement doesn't fit. There we go. There we go. Never helps to move it. So the e and the ln cancel each other out, right, when they're beside each other, and that's just going to equal 2x. And then again, ln and e cancel each other out, but this is multiplied, so multiplied by 2x, which would be 4x squared. Okay.